A 400-meter tree would be taller than the Eiffel Tower. So why has Earth never grown one? We can build towers that high. We can build antennas higher than that. So why can't nature grow a wooden skyscraper with leaves on top? The first suspect is obvious. Maybe the trunk would snap. And yes, mechanics matter. A tree is not a steel tower. It has to survive wind, storms, rot, lightning, and the weight of its own crown. Even the tallest redwoods can lose sections of their tops to wind or lightning. But the trunk is not the main villain. The real killer is water. A tree is basically a living straw system. Roots take up water from the soil. Leaves lose water vapor to the air. That loss creates a pulling force, and water moves upward through microscopic tubes called xylem. Imagine sucking water through a straw. Now imagine the straw is taller than a 100-story building. Now imagine it has no pump, no motor, and the water column must not break. That is close to what a tall tree is doing every day. The accurate version is this. Trees move water upward, mostly through transpiration pull and cohesion between water molecules. But as a tree gets taller, gravity and resistance inside the xylem make water harder and harder to deliver to the top. For every meter upward, gravity adds a little extra pressure cost. At 100 meters, that cost is already serious. At 400 meters, gravity alone would add nearly 4 megapascals of pressure demand before we even count friction inside the xylem. That is like asking the top leaves to live in a permanent drought while standing in a rainforest. And leaves cannot ignore water stress. To make sugar, leaves need carbon dioxide from the air. They get it through tiny pores called stomata. But opening those pores also lets water escape. If the top of the tree is too dry, the leaf must close those pores to avoid losing water. Here is the child-friendly version. The leaf is trying to eat and drink through the same tiny doorway. If it opens the door to bring in air, water sneaks out. If it closes the door to save water, it cannot make food as well. The accurate version: water stress reduces stomatal opening, leaf expansion, and photosynthesis. A treetop that cannot photosynthesize enough cannot keep building upward. This is why the tallest trees on Earth are not random. Coast redwoods live in a rare sweet spot: wet coastal air, fog, mild temperatures, strong wood, long lifespans, and intense competition for light. They are almost perfectly built to become giants. And still, they stop far below 400 meters. A famous 2004 study in Nature examined tall redwoods and estimated that their maximum height is around 122 to 130 meters if we ignore mechanical damage. That is astonishingly tall, but it is nowhere near 400 meters. So what would happen if a tree somehow tried? At first, it might grow taller and win more light. Then the top leaves would become smaller, drier, and less productive. The xylem would run closer to failure. Air bubbles could block water tubes. The crown would become harder to support. Wind would become more dangerous. Building the extra trunk would cost enormous energy, while the top would give less and less back. A building can be fed by elevators, pipes, pumps, wires, and outside maintenance. A tree has to build its own tower, lift its own water, repair its own body, feed itself with sunlight, and survive storms for centuries. That is the difference. Could a 400-meter tree exist in a science fiction world? Maybe. Lower gravity would help. Artificial pumps would help. A radically different vascular system might help. But on Earth, with natural tree biology, a 400-meter tree runs into the same wall again and again. Water cannot reach the top well enough for the top to stay alive and keep growing. So the answer is not simply, wood is too weak. The answer is stranger. A tree does not fail because it cannot reach the sky. It fails because, past a certain height, the sky becomes too far from the roots.